Okay, this is a substitution rule for definite integrals, and this is a little bit more complicated problem. It just looks nastier, but it's the same exact approach. And instead of just a indefinite integral, we're actually going to evaluate this at a lower and upper limit, but we're going to use the substitution rule to get the antiderivative. So looking at this, hopefully you see that, if I can get my other color, that this term has the third power and this term has the second power. So let u equal the exponent in this case. So let u equal x cubed plus 1, I'm sorry. Take the derivative. So du is equal to 3x squared dx. I'm going to solve for dx in here, and you get du divided by 3x squared. Making the substitution. So all of this is business as usual. Okay, nothing new here. Making the substitution. I'm going to exaggerate the limits here. These limits are in terms of x because all of the entire function is determined in x. So the upper and lower limits, it's important that you realize that they are actually x equals -1 to x equals 2. And making the substitution, you get x squared e to the u du over 3x squared. So we have a couple things going on here. We have the constant that we need to account for. So I'm going to pull out the 1/3 and rewrite this integral. Right, that's going to cancel out as e to the u du. But we've got a mix of variables here. A mix being the upper and lower limits are in terms of x, and the rest of the integrand is in terms of u. So we need to, there's two basic approaches. We can change the limits of integration, or we can continue the way we were and back substitute and then evaluate. So I'm going to show you the first method, and that is to change the integration limits to u in terms of u. So remember, this is this function that we defined when we let u equal when we let u equal x cubed plus 1. That's really g of x. Okay, that's g of x. So what we're going to do to change the limits of integration, which is our fifth step, we're going to plug in the x values into this function g of x and get them in terms of u. So we're going to change the limits of integration to be in terms of u. And what you need to do is just whatever you let u equal, you've got to go back and put the x's in there for the limits of integration to get a value for them. So I'm going to put them in, keep them in yellow. So this is -1 cubed plus 1, and the upper limit is 2 cubed plus 1. That converts them to u, and then of course the rest of the function stays in terms of u. So now we have a consistent set of variables. So now you can go about taking the antiderivative. But before I do that, I'm going to simplify those limits just so that I clean it up a bit. So the lower limit becomes 0, and the upper limit, let's see, 2 cubed plus 1 is 9. And we've got everything is in terms of u, which is one approach. Now you can take the antiderivative of e to the u, and hopefully you remember that the antiderivative of e to the u is just e to the u. And now we're evaluating it at the upper and lower limits of 0 and 9. So this is 1/3 e to the 9th minus 1/3 e to the 0. And recall that e to the 0 is just 1. So I'm going to just do a little bit of algebraic cleanup here. I'm going to you could find a common denominator to put them back together, and that's going to be your answer. So that's the first approach. The other approach you could have taken is right here where we actually change the limits of integration. What you could have done instead was to continue evaluating this in terms of u, but then back substituting for u in terms of x. So we're going to try that approach. So here's another approach. Another approach. And the other approach is to actually back substitute for u and then evaluate it. So taking the antiderivative, you got e to the u. And if I were to evaluate this and take the antiderivative, you still get 1/3 e to the u. I'll substitute back for u, and u is equal to x cubed plus 1. So this would be 1/3 e to the x cubed plus 1. Evaluate that, and you can leave the limits in terms of x. So let's substitute in, and this is 2 cubed plus 1, right? I'm going to drag along the 1/3, whoops, minus 1/3 e to the negative 1 cubed plus 1. This evaluates to just 0, so this term is going to go to 1, and we're left with exactly the same answer that we got using the change of variable rule for the limit. So either way is fine, and there's going to be times when it's easier to do it one way or another. You have to build up your intuition for that. But for now, I want you to take the approach of changing the limits of integration. So I want you to do this for now when you evaluate a definite integral with using the substitution rule. I want you to get used to that approach. But know that, if you run into trouble, you can try continuing and evaluate back substituting in for u and evaluating the integral with the limits of integration of x. Just be careful. All right, so I want to put a big beware here at the bottom, and maybe I'll write it in red. Right, beware. Do not mix variables. If you work in terms of u, stay in terms of u. If you work in terms of x, stay in terms of x. Okay, so no mixing of variables. You don't want to evaluate this and then, it would be an error to evaluate this integral as this, right? Because these limits of integration, all right, these are x's, and this is y, and that's u. So don't do this. That's a common mistake that I see all the time. Okay? We'll do a warm-up tomorrow in class, and hopefully you'll have a couple homework problems that you can do.